Okay, this is just a little refresher on kinetic energy equations and the way that they're derived and interpreted. This is in preparation for deriving the kinetic energy equation for a Newtonian fluid. So remember, suppose you have something really simple like a solid particle of mass m, and we're going to imagine that a force F is exerted on this particle, causing it to acquire a velocity v. Well, we can describe this process by Newton's second law in this form: d by dt of the parcels momentum, mv, is equal to the force F. Now, to get a kinetic energy equation, we multiply both or dot both sides of this equation with v. So v dot d by dt of mv is equal to v dot f. But before we write that, notice we can take the v inside the derivative like this. We can write d by dt of 1/2 m times the square of the velocity vector, v squared, equals, and now the right hand side is just the dot product, v dot f. So the thing that we're differentiating here is the kinetic energy, and the right hand side, v dot f, is kind of an old-fashioned term. It's called the rate of working. The rate of working. It's the rate at which the force does work on the particle in order to change its kinetic energy. Now, in this case, our force is acting in the same direction as the motion, so that v dot f, the dot product, will be positive, and that indicates that as the force continues to act, it increases the kinetic energy of the particle. Now, we could suppose that we have the opposite situation. Suppose instead of this force, we have now a force acting in the reverse direction, like this. Oops, like this. Well, in that case, now the force is going to tend to decelerate the flow and reduce the kinetic energy, corresponding to the fact that the rate of working, the dot product of those two vectors, would now be negative.